And of course, if you massage this further, you can write it in terms of eccentricity and such. I don't know if I have that here or not, but yeah, that's as far as I went. But yeah, I don't know who first did this, but this is, well, I think Newton did actually, but I'm not sure how Newton actually did it, because Newton, I know Newton did these things once he introduced his universal law of gravitation, but he wouldn't have done these things in terms of Lagrangian mechanics, right? Newton would have solved like Newton's second, F equals ma for the universal law of gravitation, and because he's Newton, he was able to work out the calculus that way. I mean, ultimately, you get to the differential equations that we found from Lagrangian mechanics fairly quickly from Newton's second law for this problem anyway, so it's like it's not really that different. But yeah, I think it was Newton who actually first solved this, but Kepler did not. All Kepler did was to fit a phenomenological model to data. He just had a bunch of data, and he fit the data to ellipse. That's pretty much what he did, which is phenomenal, of course, but he also was, standing on the back of like Tycho Brahe's like decades of observation. But anyway, hey, we got time to talk about homework if you guys want, or we can end early. I don't say those words lightly, but this is it. I mean, that's the end of the material for test 1, guys. So.
Let's talk about what's going to be on test 1.
What's going to be on test 1? What don't you know?
Everything.
That's what's on the test.
I don't know how to add 2 plus 2. I forgot.
You forgot how to add 2 plus 2.
Yes.
I feel like that's somewhere on the test, probably. Let's see here.
Could you look at problem 35?
Yes. Okay.
Can you solve the problem 35?
Sure. I could do that. Probably.
Show us what you solved.
Yeah.
I can at least start us. All right, so problem 30 and 5. Boop, 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 boop. So we have f of x, y, z equal to 1 plus y squared divided by 1 minus 2xz. What even is the problem here, though? Calculate the multivariate Taylor series centered at the origin. Now, to order 4. Now, if we were to, if it's a critical point or not.
If it's a maximum.
So, one way we could do this is we could look on my notes, and I have a formula for the multivariate Taylor series up to order whatever. And if we were to accept our fate and do it that way, that would be very foolish, because then we would have to calculate partial derivatives up to order 4 of 3 variables, which is a lot of differentiation. And this is a rational function too, so it's quotient rules even at the start, and it just gets worse from there. That is obviously not how we should do this. What we should do is use the principle of calculus works like it should, which is to say you can use substitution of calculus 2 stuff that you already know. So what this is 1 plus y squared, right, times what? 1 over 1 minus 2xz. But this is 1 over 1 minus r, which is 1 plus r squared, and so forth and so on, by the geometric series. We know geometric series?
No.
We don't. Oh no. Well, that is unfortunate, because not knowing the geometric series is very dangerous for my examples.
I recognize it. It's a good thing you wouldn't put geometric series on the test.
Nicely played, Sam. Nicely played. That's funny.
Because now we know what to do. No, they're terrible.
So the geometric series, guys, is just if we have a plus ar squared plus ar cubed plus dot 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 dot, that's equal to a over 1 minus r, given that the magnitude of r is less than 1, right? This is the geometric series. So, yep.
Should that end in AR?
Hmm?
AR.
Oh, yeah, I don't know what's wrong with me. Well, many things, but yeah, let's try this instead. There we go. Thank you. Okay, so great. So this is 1 plus 2xz plus 4x squared z squared plus stuff that's higher order than I care about. I think if I do any more, I've solved the problem. Maybe. You're like, you can do that, right? No. So we're supposed to find the multivariate Taylor series centered about 0, 0, 0 to order 4. All right, so we just need to multiply. So then what you do is multiply. But you multiply only keeping up to order 4. So obviously 1 is part of the story, right? 1 times 1. Then 1 times 2xz. That's quadratic, so we'll keep that. How about y squared times, now 1 times 4x squared z squared, that's quartic. I'm going to come back to that. Y squared times 1 is also quadratic, so I'll put that here. Y squared times 4x squared z squared, that's 6th order. I don't care about that. That's higher order than I care about. So what am I missing? Plus what? So unless I've missed something, I think that's everything. That's all terms up to, quartic order. Am I missing something? I might be missing something. What do you think I'm missing? Oh, how about that y squared times xc? Oh, I do need that, right? That's 2. That's also order 4, isn't it? Yeah. My bad. So 2 x z y squared. Yeah, that's still order 4. Is that everything? You gotta be careful. It's easy to miss stuff. You could just multiply everything out and then just erase the part. So what do you guys think then? Is it a critical point? Is 0, 0, 0 a critical point? What is the gradient of f equal to? So there are no x, y, or z terms on their lonesome here. So I can read, looking at the general multivariate series, that this is 0, 0, 0, which is to say that, hey, guess what? It's a critical point. All right? Now I'm faced with the question of, is it a max or a min? How do I judge that? Yeah, I got to look at that part. So this is going to define my quote-unquote Q matrix, like you said. This not relevant. Relevant. Yeah, fine, good enough. Not relevant. So my Q matrix is what you got here? A 0, 0, 1, 1, 0. Looks like we got a 1 up in here. Oh, funky. Yeah? So at this point, we need to find the eigenvalues of this. So okay, so if this had been just sums or differences of squares, then we wouldn't need to go and do linear algebra at this point. We could just read from it what the story was, right? Like hypothetical, if I had g of x, y, z is equal to 47 minus x squared minus y squared minus z squared plus x to the 432nd plus dot, 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 then I just look at this and go, oh, gradient of g at the origin is 0, right? And apparently, g of the origin is 47, and that's a local what? Max, right? Because all of these terms are taking away from 47 close to the point. With this expression, I don't know offhand what's going on. So what I want to do is find the eigenvalues to go back to that whole quadratic form thing. So what are the eigenvalues of this? So here's some, so like, it's nice to find a shortcut so we don't actually have to do that, right? So here's some fun facts for you. The determinant of a 3 by 3 matrix is the product of the eigenvalues. The trace is the sum of the eigenvalues. And this is, since A transpose equals to A, that implies that lambda 1, lambda 2, and lambda 3 are actually all real numbers. So we have all this. Here's some pro tips from linear algebra land for you. These things we could use to circumvent the actual calculation, perhaps. What's the determinant of Q? No. -1. If you want, flip the first and the third columns and then the determinant down there. Anyway, or do a column expansion, whatever is most natural to you. That's -1, right? So -1 is equal to lambda 1, lambda 2, lambda 3. What does this mean? Actually, I don't know. Oh man, it could be that they're all negative. Right? It could be 2 positives and 1. Yes, Daniel.
But you said the trace is lambda 1 plus lambda 3. But the trace is just 1.
Oh. So the trace is 1, so they can't all be negative. Can they? No, if they're all negative, the trace has to be negative. So at most we could have 1 negative and the other 2 positive. Anyway, the point is, the point is that this is enough data to see it's a saddle point.
With the other one,
But
they had 2 positives and 1 negative, and that
2 positives, 1 negative, saddle point, yeah. Now, of course, we could actually just also work out the characteristic equation here. It wouldn't be that hard, right? And that probably would be healthy for us at this moment, as opposed to me trying to circumvent all manner of difficulty. And so what all that means is we could choose eigencoordinates, and this expression can be rewritten as 1 plus like x bar squared plus y bar squared minus z bar squared plus higher order stuff, right? So it becomes manifest that this is a saddle. But we don't need to go into all this detail, right? If you can come to a reasoned argument that we don't have all negative or all positive eigenvalues, right? But they're all non-zero and they have different sign, that's enough to show that it's a saddle point. Yeah.
How is it this equation is symmetrical in x and z and yet has a different response? Oh wait, sorry, those are x bar and z bar. Okay, never mind.
Other questions? So, like for problem 36, well, I may not hurry through it. I think that's very similar to problems that are already worked in the notes, so you probably get it, hopefully. Okay. Does that make sense? Like 34, 9,000. I can tell when I wrote this problem. Power level 9,000. Let's see here. That's not for you to know. It's a shibboleth. It's a saying which is known to members of a community, and to those who it's not known to, it's to identify them as outsiders. So I think in problem 34, there's no linear term, so that's going to be a critical point. I think the critical point is like, oh yeah, 1, 0, minus 2. Oh, it is. Notice it is. I say it is. Duh.
You have to analyze it.
Analyze it.
I did that earlier today. We'll see.
Cool.
That's why I asked if there were two positives and one negative. Does that make a saddle point?
Oh, okay, good. So that one you actually need to do. That one you do use technology for, or whatever.
Well,
but.
I did cofactor expansion until it got down, and then I did algebra to get it down, and then I used my calculator for that.
Okay.
Took the eigenvalues from with the calculator.
So how about this? Since all right, so
Off the top of my head to use.
here's something I can do to reduce the stress on the test coming up. Like, I won't ask you to calculate eigenvectors and eigenvalues on the test. I'll give like if there is a problem like that, I give take home. So that part of the test you can just, do take home and give it back to me like Wednesday or whatever. It shouldn't take terribly long. And that way my matrices can be ugly too. Hey. But, which I'm not saying that there's not going to be matrix calculation on the test. I'm not saying that. I'm just saying with respect to the eigenvector, eigenvalue calculation, I won't put that on the test. Well, there's got to be there's Jacobians. Like, there will be Jacobians, right? And but there's also differentiation, which is not, about Jacobians, right? Like the aha problem is the one that always comes to mind, like the differential of the square, matrix square. Oh, by the way, if you had a function, you can also define Lagrangian density, which is a function of like perhaps a field and space-time, and then integrate that over four-dimensional space-time. And I think if I remember right, you get equations like partial L partial A mu is equal to partial x nu of partial L partial partial nu of A mu. So these are the Euler-Lagrange equations for like a field. So these things continue to generalize for like more interesting, deeper things. There are like Euler-Lagrange equations for functions. So like our Euler-Lagrange equations had just one independent variable, time, and multiple dependent variables, which we call generalized coordinates. These are Euler-Lagrange equations for 4 independent variables. This is summed over. So these are like the, these actually would give you relativistic or Lagrange equations actually. But anyway, I have no homework problems on that. Just saying. Oh, your homework. Yes, your homework. I know your homework. I'm sorry about the homework. I do have solutions written for everything except for mission 5 at the moment. What's that?
Don't have my homework?
I have your homework. That is true. I don't have your homework.